Hello, welcome to chapter 5 in the Digital System Design course. And in this chapter, we are going to discuss spatial spatial design. Just to clarify the term, spatial means parallel. Okay, so here, uh, parallel, parallel design. So spatial means parallel. And obviously, why do spatial? Because we need speed up. Okay, we need to speed up design. Parallel design or spatial design, we need to speed up the design. Now, in this chapter, we'll discuss three things. We'll talk about some principles here as an introduction. We'll talk about how to identify parallelism in a design, because inherently every design, um, as humans, we think of designs as sequential, so we need to identify those opportunities for parallel design. And then we need to talk about parallel design or spatial design in platform FPGA. We'll start today with the principles, and we'll talk about a few topics here. Okay, we'll leave the other topics for other lectures, as the identify and the spatial design in FPGA platform. But in terms of principles, we will talk about the granularity, granularity, which means the level of spatial design. We'll talk about the degree of uh, uh, spatial design, and we'll talk about the organization and the control of the uh, spatial design. So four subtopics underneath the principles. Okay. All right. So let's get going here. Okay. So spatial design, basically, um, we are talking about a spatial design when we are um, typically we are running things on a single thread, single microprocessor, where things are executed sequentially. Okay. Where spatial design really talk about multiple threads, multiple um, processing units executing threads simultaneously, and all of the purpose of that, I would like to have some kind of concurrency which will speed up my design. Here's an example. If you do a linear search, let's say for example you have 8 items. Okay, if you want to search one item amongst them, so you have to kind of march over those linearly, and the complexity of your search will be what? Will be of order of n. Big O of n is a class of an algorithms that grow linearly with the number of the data that you are searching within it. Now, suppose you change your to binary search, and binary search, what it does is, it really does build a binary tree where you kind of you do a comparison between two, and then move through down this tree. Okay, and notice that the height of this binary tree is log, okay, of n, and that reduces significantly the speed of your search. And obviously, if you could do those in parallel, okay, you will significantly reduce your time to search your to search for a single item. Now, if you could do all in parallel, then your big of O will be of 1. Of course, when your list of things grows into uh, millions and billions of items, such full parallel search is not practical. Okay, so basically, this is what spatial design is. It is simultaneously, concurrently doing things to achieve speed up. Okay, now, so let's talk about the idea here. Let me illustrate it with a graph. So suppose, for example, you have a program, and this program, let's say T, and we will call that a task. Okay? And this consists of subtasks. Okay, that uh, uh, um, task. Let's see, T0 or subtask. Sorry, T0, subtask T1, all the way to subtask T7. And if you execute these subtasks sequentially, notice the word sequentially, you will need 8 time units for this program or task to be completed. Well, somebody might come up with another idea and says, well, how about we parallel process these subtasks? We break our program T into um, into different, um, let's say, cluster of subtasks that can run on these units. So this unit could be a microprocessor 1, 2, 3, 4, and on microprocessor 1 or CPU 1, we can run T3 and 2 T2 and T6, and on this one, T1 and T5, etc., etc. Now, with this parallel execution, I need 3 time units. So obviously, there is a speed up here that I have achieved, and the speed up equals 8 over 3, and that this gives me a speed of 2.1. Now, someone might say, so how about this T7, right? If I could take this T7 and place it here, and because notice T7 is pushing out, then I could finish the execution in just 2 time slots. Now, in this case, the speed up will be 8 over 2. This equals to 4. Of course, this all depends on how we programmed our subtasks and what are the relationship between them, etc., dependencies, etc., etc. But this is what if we could do that. Now, so the idea is the more you can have parallel units and the clever split of task between all of those, the better it is for your speed up. Okay. Granularity talks about what are the levels of this. Remember that we talked about T, which is the task, consists of subtask T0, T1, all the way to T7. The question is, what are these subtasks in relationship to this T? Is T a program or an instruction? Oh, well, it turned out that you can go fine grain with these things or coarse grain with these things. And let's just illustrate this with this table. In this table, we show the granularity. The T here can vary from operation on scalar values all the way to multiple threads. And therefore, the subtasks can vary from bit fields operation all the way to a single thread. Over Overall, it is easy to implement the ones on the top but you will get more speed up if you go down in the list. You'll get more speed up. So here is your trade-off. So let's go over those very quickly here. So bit level, you can look at the T here is a connection of operations or a series of operations, scalar values, ANDing, ORing, and in this case, really you can have um, the subtasks are operations on the bit fields. Now you could do that independent of the application. You don't have to think of your program what it does, but it is limited. You have limited parallelism. Obviously, if you go up with the um, granularity, more you can think of T as the program as a whole, and you can think of the subtasks as the instructions, and you can have parallel instructions, and in this case, you can increase the parallelism. Of course, you can do so much, and then you have to go to from the instruction level, so bit level, instruction level, to the iteration level or the data level. And in this case, T becomes operations on vectors as opposed to scalars. Okay, so vectors and scalars. So the more you go vectors, now the more you have parallelism. Now we can think of the subtask as a really sequence of instructions. Whoops, sorry. As a sequence of vector instructions. Okay, here's an example, right? And finally, the level of parallelism can go to the thread level. Notice how we progressed: bit, instruction, data, and thread. And here your task becomes really multiple threads, and your subtask will be a thread. And here where you get the most speed up, but this is will increase the difficulty of your design, obviously. So the second point after granularity is the degree of parallelism. And notice here what we are doing here. We are basically plotting the number of parallel threads that we could do in a program. Okay, so suppose we are running parallel threads and we're plotting per time. We started at time zero. At time zero, we were able to run one thread. Time two, between 1 and 2, one thread, between 2 and 3, one thread, and between 3 and 4, we were able to run two threads. Between 4 and 5, we are able to run five threads. Between 5 and 6, we are able to run six threads, and 6 and 7, six threads. And this is what our application allowed us. Then we can say that the degree of parallelism in this program is that maximum degree of parallelism, we are able to run six threads in parallel. That's important. Why it is important? We'll see in just a second. The average degree of parallelism is we take this area, okay, under the curve, and we divide it by time, and we end up with 3. We say that the average degree of parallelism is 3. Now, why these two metrics are important? Well, first of all, maximum parallelism sets the limit on how much I can gain by adding hardware units. So for example, if you have hardware units that can, 6 hardware units, you can execute those 6 threads. But if you have 7 hardware units, the 7th hardware unit will not be of any use because maximum threads that you can execute in parallel at any time is 6. So it sets the upper limit on how many hardware units you can add to speed up things. Now, the average parallelism is more of the practical measure. It says, you know, yeah, you can speed up things by adding 6 hardware units, but on average, really, you are not running 3 threads. So you are going overboard by having six hardware units. Most likely, between 3 and 6 is your optimum point. So right here we say that if having 4 cores instead of 6 would would achieve 80% of the performance and with the 66 resources. And as I said, going for maximum number of hardware for maximum number of hardware units to achieve maximum degree of parallelism sometimes hurt you in terms of producing a very expensive hardware without getting gains from the hardware. Now, the third point we want to talk about is the organization. How this spatial or parallel processing is organized. Typically, in any computing system, you have instruction pool. You can think of this instruction memory and data pool, data memory, and some kind of processing element. And this processing element can be a CPU, can be a simple processing element, where data, where instructions are fed to this processing element, and data is fed to this instruction element. Now, in in the general purpose instructions that we have, typically you have single instruction, right, and single instruction stream and single data stream. These are the typically the general purpose processors that we are using in our simple embedded systems. However, what you could do, for instance, is you can have multiple data streams. So you can have these CPUs replicate them, or processing element replicate them. And in this case, once you replicate the CPUs or the processing elements, you can have multiple data streams, okay, like in this case, with single instruction stream. So in this case, what you have is you have a single instruction stream and multiple data stream, okay? And and this is basically when you are running the same instruction on large pool of data. So you're parallelizing that operation on a large data. You can think of this data, for example, as an image. So you are really have large image where you are doing the same kind of operation. You're just kind of splitting that image into parts and blocks, and you're parallelizing it between these processors. Or you can think of these processors. They are working on a single stream of data, but they are doing the different instructions. So in this case, what we have multiple instruction streams and single data stream. Okay, and in this case, this is more of the systolic processors operation. Okay, and in this case, really, you're trying to speed up running the speed up executing the instruction, versus here you're trying to speed up executing the data. You have too much data here. Here you have too much instructions. You're trying to speed up execution. Finally, we have multiple instruction streams and multiple data streams. And as you can see that in this case, we have processing elements. Everyone has his own instruction stream and its own data stream or its own memory. And the communication between processing elements typically done via specialized communication links or higher memory level. So these are the different uh, organizations for spatial designs. Here are examples for that. For instance, when you're talking about the single instruction stream, multiple data stream, uh, these are these are typically your vector processors or stream processors, and both of them are similar, except the the in the vector processor, the compiler has more active role in implementing and detecting parallelism. In the stream processors, however, the programmer identify kernels in the program, explicitly identify the kernels and map them to the local memories of the processor. So it's really more of the how much the programmer is involved here that differentiates between the vector and the stream processor. The vector mostly a compiler role here, stream processor mostly programmer role here. In MISD here, the multiple instruction stream, single data stream, it is more of the systolic processor, and in multiple instruction, multiple data stream here, it is more of an array processor. Um, and you can think of one type of the of application where the same instruction stream is replicated to all the processors, and this is called single program multiple data, single program multiple data, or data parallel programming, which maps to this type of hardware. Okay, so these are examples of the organization of spatial design. One thing about pipeline design is that we have inside the pipeline design, as we have taken in other courses, that the design is the hardware design is split into in stages. And typically, what you are trying to achieve here is that you are trying to finish an instruction every clock. So really, your throughput should approach to one, and your speed up under when you have lots of instructions, it should be equal to n. Okay. Similarly here, whenever you have multiple threads here, yes, you do have those idles, but over good scheduling, you can have a speed up of the system equal to the number of threads. Okay, and here is we move to the last point here, was the control of parallelism. How do you control this parallelism? And he's giving here an example of finding the roots of this polynomial, which is ax squared plus bx plus c. And we all know that the roots are computed with this equation. Um, there are two roots, obviously. And what we would like to do is that we would like to write this into some kind of a program where it computes, first of all, this square root, okay? And then we compute the denominator here, okay? And then we compute x, right, 0, and then x1, 4 instructions, okay? So when we do that, we can see that with this 4 statements, we can parallelize the execution of the denominator and the descriptor, okay? And then the computation of x0 and x1 can be also parallelized. And you can see that here we are able to achieve this level of parallelism. Now, this is at the granularity of the statement. Well, how about if we go deeper, lower into the operation granularity? So we uh, we, uh, we we split the statements further into operation, the multiplications, and this is obviously b is computing b square, and here is computing a times c, and this is for ac, and then this is the subtraction here, which is we have b square minus 4ac, this is the square root, etc., etc. You can see here that I can achieve higher level of operations, parallelism of operations. And this is because I was able to explore more of opportunity for parallelism by splitting these statements. Now, data parallelism instead of instruction parallelism, this is more of vector operation opportunity. Whenever you have vectors, dot product, matrix multiplication, this is where you can see there is this regular parallelism, because what we just looked at here is this is instruction, more of an instruction parallel based on instructions, and this is kind of irregular or ad hoc parallelism. Versus here, when you talk data, they should easily be parallelism should be easily explored within the loop between the vector operations and much more opportunity for parallelism and speed. With this point, I conclude the first part of chapter 5, where we talked about the principles of spatial design. And thank you very much.